Next, we'll be talking about ions. Now, this one we're going to alter atoms. Remember, atoms contain the same number of electrons as protons, so they're neutral. We're going to disrupt this. Ions are formed from the gain or loss of those valence electrons, the outermost electrons. So we're going to start off with two atoms. First of all, lithium, remember, atomic number of 3, so it has 3 protons. A rule of thumb says 3 neutrons and 3 electrons. Remember, only 2 fit in the first shell. The third one has to go in the outermost shell. Also, fluorine. Now, fluorine has atomic number of 9. And so we have 9 protons. The rule of thumb says 9 neutrons. And of course, 9 electrons. We have 2 in the first and 7 in the second shell. Do a little bit of counting here. Lithium has 3 protons, 3 electrons, having a neutral atom. Fluorine has 9 protons, 9 electrons, a neutral atom. I stated before that what drives chemistry in the universe is that everything wants a full outer shell, like the noble gases like helium and neon and such. Now, lithium here has its outermost shell that can hold a total of 8. So it could go around trying to find 7 more electrons. Keep in mind, electrons on our planet, this is not the star. This is not like our sun. There's not electrons necessarily just zipping around all over the place. Electrons are usually on something. They're on atoms. They're on ions. They're on isotopes. Okay, they're already involved in something. They can jump from one to another, usually short time, short distances. Trying to find 7 electrons is going to be quite difficult. So instead, what it could do is get rid of 1, and underneath that shell is a full shell. Fluorine has 7 in its outermost shell. Now, it could try to get rid of 7, but that's going to be difficult. Instead, of course, the easier way is to find 1. Add 1 more, and it has a full outer shell. If lithium and fluorine come in close proximity to one another, they come to a little agreement. Lithium needs to get rid of 1, fluorine needs to get 1, and so they work that out. And what will happen, nearly the speed of light, that electron will jump from the one atom to the other. I slowed it down so you could see it. That changes our counting, though. Notice what changed. Only the number of electrons and those valence electrons, because those are the ones that can move. We can't change the number of protons because that would change the element. That would actually, what we call alchemy. You could literally change lead into gold. And if you could figure out how to do that, make some machine or some process to do that, do not file for a U.S. patent. Because U.S. patents that you file for cannot violate a law of nature. Laws of nature, as we know them now, that cannot happen. So if you do that, they will not grant you a patent, and they will simply publicize, hey, and let everybody know this is how you do this, and gold will become worthless. Instead, come and find me, and I will help you, and we will make lots of money. We cannot change the number of neutrons. This is not atomic physics. Okay? We can't change the inner ring of electrons. Those are placeholders. The only thing that can happen is allow for exchange of these outer valence electrons. So we still have 3 protons, but now only 2 electrons, so we have a net positive 1 charge. So that's an ion. Fluorine still has 9 protons, but now 10 electrons, so a net negative 1. If you add these two together, it's still neutral. We haven't added or depleted anything from the system. We simply rearranged them. And actually, nature did that. Keep in mind, a lot of times I think chemists get a little bit full of themselves and thinking they have way too much control of things. You do have some control. I mean, you can have lithium in one hand, fluorine in the other hand, and yeah, you have control. But it's not like one of those stupid pet tricks of David Letterman's that when you put the little biscuit on the dog's nose and you tell it to wait until you snap your fingers, then it takes it out of midair. It's not like that. It's more like a gun. You have control over it. But once you mix lithium and fluorine, you don't say not yet, not yet, not yet, and tell it when to start reacting. It will automatically, like when you pull the trigger on a gun. You have control of the trigger. But once that bullet comes out the other hand, oh wait, that isn't what I meant to do. Come back, come back, come back. You don't have control anymore. Chemistry is the same way. We have control up to a certain point. But once nature takes its course, we can't do too much about that. Always keep that in mind. That's why it's very important to know what you're doing in chemistry. So these now have charges on them. Now if you don't write a number behind it, you assume a 1. So this is lithium plus 1, fluoride minus 1, okay? And of course, gee, these are oppositely charged, and what do oppositely charged objects do? Of course, they attract. And so this is our first type of bond. We'll talk about ionic bonds, and those are involved in things like salts. And so these will come together and hold together like little magnets. Now some terminology here. Oxidation is going to be our term for the loss of one or more electrons, and it's going to make something positively charged. Reduction is the gaining of one or more electrons and will cause something to become negatively charged. Now if you have a problem with that second definition, good. Reduction is the gaining of one or more electrons. If you remember those ancient Greeks we talked about, those brilliant scientists and such and creators of modern chemistry, again, they theorized about atoms and they were right. They actually theorized about protons and electrons and they were right. And chemical reactions that now what we call electrons actually move between the two atoms, they were right. Now, which direction do they move? Their basic chemical test was throwing stuff into a kiln, into a fire. Said you do a hardness test on a scale, of course diamonds being the hardest. You do a streak plate, a ceramic plate, streak it, see if it scratches, see what color the streak is. And their basic chemical test, they would take something and throw it into a fire. Does it burn? Does it not burn? What color's the smoke? Does it melt? Okay, what color's the ash? All that stuff. That's their basic chemical test with oxygen. So they called that process oxidation. Now I knew something was gaining electrons and something was losing the electrons. So which was which? They got it backwards. They had a 50-50 chance. They got it backwards. So that's why this is reversed. Now, why they never changed that later on when they figured out, oh, that's backwards? Again, tradition. A lot of people knew about that. If they changed the definition for years, there's going to be confusion. And so they just never changed it to be correct. When you dissolve salts into water, you get electrolytes. And you've heard a lot about electrolytes. Okay, you need electrolytes. And you learned a lot in AP1 why you need electrolytes. To create those currents now. We don't run on electrical currents, we run on ion currents. And so they carry electrical charge when placed in water. Water itself does not carry electricity. Okay, salts do. Remember how we made salts, gaining and losing electrons. Electrical current, as we talked about in AP1, is, well, this is AP1, sorry, as we're talking about in AP1, jumping from ion to ion. Because remember how ions are formed by gaining and losing electrons. So they can jump. So basically the more salt you put into water, the better it conducts electricity, because basically you're adding more wires. And that's why in fresh water it contains a low amount of salt. And you can still get electrocuted, but it doesn't carry electricity as well. And if you're in salt water, it will conduct electricity a lot more, and you're more assured of being electrocuted. This is why in our safety classes and such, we get told, during electrical storm, do not take a bath. Because even though you have fresh water in the bathtub, if lightning hits your house and it finds your pipes and comes down the pipes and finds you in the tub, here's this nice tub full of water. Don't forget, the reason why you're taking a bath is because you're probably dirty, and one of the ingredients in dirt is salt. Maybe you're just working out and you're sweaty. What's in your perspiration? Salt. And if you're using soap, salt. And so now that water is very salty and can conduct a lot better and of course electrocute you.